Question 7, check out the playlist for the other questions. We covered them. I actually already did question 7, but my video failed, so I'm just going to do it again, and hopefully I give a better explanation, and just extra practice for me. So 2 machines are used in a factory to manufacture semiconductors. Machine A manufactures defective semiconductors 10% of the time, while machine B manufactures defective semiconductors 5% of the time. Okay, a randomly selected machine manufactures 10. So we're choosing one of these machines, A and B, A or B, and one of them manufactures 10. And so the chance is 50-50, so 50% for each. Both machines are equally likely to be selected, and that's where that comes from. Find the probability that exactly 2 semiconductors are defective. So what we need to do is, this is our binomial distribution, right? And let's use our notation. So we have X machine A, machine B, so XA is our binomial, and we have NP, right? And so let's define that for each. So we have N is equal to 10. That's the same. That's the amount of trials, right? 10 semiconductors. We're having 10 trials. And then we have probability of success in making a defective semiconductor. So here success is ensuring we have 2 semiconductors defective. So that is, this is A, so we have 10%. So let's do 0.1 probability of success. And then we have XE, and that is N is equal to 10, P is equal to 0.05. Same reasoning, except 5% of the time. And now we are told that we want exactly 2 semiconductors to be defective. And so our probability that XA is equal to 2, right? That we have 2 defective pieces out of 10 trials is equal to our 10C2 and then our probability of success, that's 0.1 to the power of 2, right? We want 2, 2 is our, okay, let me give you the formula so you guys understand what we're doing here. But you guys should remember this by heart. So we have our probability of success, and this is R, this is R, and this is our N from our binomial formula. And then we have 1 minus P to the power of N minus R, right? This is our binomial formula from our binomial theorem. And so we're essentially using this to solve our probability. And so I'll just erase that. Sorry, my computer's a bit slow. Okay, so 10C2 P and then 1 minus P, that's 0.9 to the power of 8. And so this essentially is like 2 trials are being defective, the rest are not defective. And now let's do PXB is equal to 2. That is equal to the same thing, but this time we have a different percent probability rate, and 0.95 to the power of 8. And so let's find our answer to both of these. And I did that already, like I said, and our answer was 0.19, using our calculator, 0.1937. So definitely try it out yourself and compare 102,445, right? I'm just showing you all the decimal places so that you can compare. And then our next one, how would I just bring this here? Let me copy. Okay, copy, and we bring that here. Okay, it's a bit slow, so I'll just write it down. 0.0746347,985, and I missed a 2 back there. So that is what we get if we use our calculator. And now let's go understand the rest. Probability that we have two defective overall from this random selection of the machine is now equal to half, right? Our probability of choosing a machine is half. So half times what we got here. So let's just say pxa equals 2 plus probability of pxb equals 2, right? So we're taking the half, we're summing the halves of these probabilities, and that gives us the total. And so we just have to solve that, and I have done that. And it's just plug and chug, right? So let's use our value 0.13411725. 0.1347411725. 41725. Right. And ideally we should be using all the numbers in our calculator and storing that so we can use it later. And we put this to 3SF, so 3SF, there you go. So that's our answer for A. Now we have B. B is, given that exactly two semiconductors are defective, find the probability that they were manufactured by machine A. So what they're essentially asking here is, given we have two defective semiconductors, so our given is two defective, find the probability that it was machine A that created those two defective semiconductors. So probability XA, we can say XA equals 2, but actually it's half, right? So what we can say is A, and our probability of A equals 2. A equals 2. The probability of A equals 2 is half 0.5 times probability XA equals 2. And this is just to show you guys what notation I'm using. And so it would just be 0.5 times 0.19371024445, and that should come in handy when we do this. This is our conditional probability equation, and so what we know is it's A intersection B, right? And so we have A is equal to 2 intersection 2 defective, right? And that's divided by, sorry, this should be A. So probability of A is 0.5. Probability of A, choosing A. Let's make it as clear as possible. Choosing A is equal to half, and probability that A is equal to 2 is all of this, right? And what is this? This is probability 2 defective. Hopefully that makes sense. And now, what exactly is this? Right, this is our independent event formula. Now we can just do probability A equals 2 times probability 2 defective. But actually these are not independent, right? So A is equal to 2 is part of 2 defective, so all we have to do is do A is equal to 2, right? So we have, if we have a Venn diagram, we have probability that 2 defective, right? And then we have a smaller one inside, probability that A is what causes those 2 defective pieces. And so essentially all we need is just that, because that is the intersection of both. And then we have probability 2 defective is our total. That is 0.134. That is for both A and B. We have b here as well. Probability b is equal to 2. Sorry. Okay, so we just use that, and that's our formula. And we have this here, so let's put that in. 0.5. And I'm just being very explicit with my steps so that it's easy for you guys to follow. But we need to be much faster in the exam. 1, 0, 2, 4, 4, 5. And use your stored values, of course. 1, 3, 4, 1, 7, 2, 5. And that gives me, let me check, 0.5 times 0.1937102.445 divided by 0.1341725. That gives me 0.7218.7, right? And that is equal to 0.722 to 3 SF, always 3 significant figures. And that is our answer. Hope that makes sense, guys. Now I'll be moving on to question 8. Yep. Yeah, so like I mentioned, I started our video for question 7 and 8, but it seemed to have failed, as you can see from my laptop. So I'll just go through this again. The following diagram shows the graphs of two functions. F of x is equal to this, g of x is equal to that, and we're told that they intersect at this point. And this region is rotated 360 degrees about the y-axis to form a solid of revolution. Now we just have to find the volume, and this is what the shape looks like, right? Yeah. So all we have to do is find the volume, and that's just integration, right? But we need to remember when we're doing a revolution, that's pi. Let me just see if there's, yep, that's it. Okay. So we're given y, but it's revolved around the y-axis. Now we need x in terms of y. So let's do x is equal to, so looking at this, y squared plus 16. So y squared plus 16, and then root, right? So we're rearranging to make x the subject, and then we have x2 is equal to, and x2 is for g of x. So that's this, right? And I hope you guys understand what we're doing with y here. We have this shape, right? And we want this area, but we have, how do we find that? We have to subtract the area under gx, right? To find that. So the area under fx minus the area under gx. So basically this minus gx. But now we're talking about the volume. So then we square that, and we have a pi squared. Sorry, pi. Right? Hopefully that makes sense. And then all we have to do is find these in terms of x. So actually this should be f y. This should be g y. And then we should have dy. And so now I'm going to do, how about I name this fy? Fy is equal to x, and gy is equal to x, right? And what we have is y minus 2 times 25 square root. So y minus 2 times 25, y minus 2, right? And I can expand that maybe. 25y minus 50, and that's good. Now all we have to do is, sorry, pi, and we're essentially talking about r squared, right? And r is our graphs. That's why our integral kind of looks familiar to our area formula. And so all we do is use our domains. So they intersect at 5, 3, and they have different bounds, right? We're talking about this bound, and then we're talking about this whole domain or range. And so we have to separate this into, how about we just do it here? 0, right? This is 0. This is, we have to find it. And so when we put 0 into g of x, we have g of 0 is equal to 2. So that's our bound. And then we can put in g of x. But first we want to be doing